Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 33, Search in Rotated Sorted Array. The problem description tells us that we're given an integer array called nums, which is sorted in ascending order with distinct values. And prior to being passed to our function, nums has been rotated at an unknown pivot point. So we want to, we're told that we want to, we're given this array of nums, which is rotated at a certain pivot point, and we're also given an integer target, and we want to return the index of the target if it is in nums or -1 if it's not in nums. And we must write an algorithm with big O of log n runtime complexity. And this is basically the tricky part here is writing an algorithm in big O of log n time, because yeah, sure, we do have a linear list, and we could just do a single iteration and in big O of n time, and linearly go through the list and then find the number. But that would be big O of n, which is not what we want. We want a much smaller big O of log n runtime. So how are we going to solve this problem? Well, when we don't have, when we need to go to sub big O of n time complexity speeds, we want to be looking at an algorithm which would facilitate that. And what algorithm would facilitate that in searching? Well, it would be binary search. And binary search is amazing if, and it's a lot less complicated if we just have like a linear, a normal list which is not rotated around a pivot. If it's rotated around a pivot, it just kind of makes it slightly more complicated, but we can still use a binary search problem to solve this. So let's actually look at this example, right? We've got, I'm actually just going to copy this. So we'll copy this and we'll put this over here. Fantastic. And then we shall say, okay, so how, where is this pivot point? Because this is what we want to figure out. We want to figure out where the pivot point, and just by looking at it, we can say the pivot point is here. But how will we actually know this programmatically? Well, we'll be able to say, let's say our midpoint is here. We'll say, is our midpoint greater than or equal to the left, the number at the left pointer? And if it is, that means it's in the left-hand side. If it's not, then it means it's on the right-hand side. So if the number is, if the midpoint was, I don't know, 1, for example, and the left point is 0, well, the leftmost point is something else, then we would know that we're not at the left-hand side, we're on the rightmost side of the binary search. So that's basically how we're going to solve this. So what can we do? How can we actually go about solving this? Well, we've figured out where our midpoint is, right? We'll just kind of mark it here. So this is our midpoint. So now we know where our midpoint is. So if our midpoint is 7, it's in the left-hand side. If the midpoint is 0 or 1, it's in the right-hand side. So now we need to search based on this. So now we have critical information telling us which side of the pivot, is the section, is our midpoint actually in. Well, if our target was 7, we would say, is 7, well, actually, let's say our target is 0, right? If our target is 0 and our midpoint is 7. So our midpoint is 7. Is our target less than or equal to 7? Oh, is it equal to 7, first of all? No, it's not. So they must be less than 7, right? Because 0 is smaller than 7. So we want to look on the left-hand side. However, that's not the case here, because we can see that we actually need to look on the right-hand side, because, there's been a rotation around a pivot point. So how can we actually, handle this case? Well, we can say, is 0 less than even the smallest number at the left pointer? If it's smaller than the value at the left pointer, it means we need to wrap around and look in the section adjacent to it. So whenever we want to do the traditional check, which is, is it less than the point that we are at? Is it less than our midpoint? But also, in the case that, is it past our left pointer such that it wraps around to the other section? So I hope that kind of makes sense. Let's look at another example. So in this example, let's say we've split up here because we've realized that this is going to be our next binary search window, and our midpoint is here, right? So first of all, we know that we are in the right-hand side, and with that information, we can say, well, okay, actually, let's say 6 is our target and our midpoint is at 1. Well, then we know that 6 is on the left-hand side. Is our midpoint is less than 6, therefore we should look on the right-hand side, is what we would say. However, we can see that would work for 1 and 2. If our target was 2, or if it was 1, if it was the midpoint itself. But after that, it wraps around to the left-hand side. So we've basically rotated around the pivot point. And because of that, what we want to do is say, let's actually, let's look on the left-hand side. So instead of, traditionally looking on the right-hand side, let's look on the left-hand side. So that's basically the logic. We still keep in mind that, it could be greater than, so the traditional is greater than or less than check. But in addition to that check, we also want to check, is our number, or is the target we're looking for greater than even the rightmost value at the right pointer? And if it is, then it means we need to loop back around to the left-hand side. So that's the logic. A bit confusing, a bit, there is a minor difference, or you could even say a major difference in a traditional binary search problem. But yeah, let's actually get to coding it. I think it'll make more sense when we actually code the problem, the solution up. So the first thing we want to do, of course, is set our left and right pointers. The left pointer is going to be at 0, and the right pointer is going to be the length of nums minus 1. So now we've got our left and right pointers while left is less than or equal to r. So if, first we want to get our mid pointer. So mid pointer is going to be equal to the left pointer plus the right pointer divided by 2. So if the target that we are given is equal to the number at midpoint, well then, happy days. We've found the midpoint, we found our target, we can just return the index of the midpoint. However, let's check, is it in the left sorted position? So if it's in the left sorted portion, we can say if the number at mid is greater than or equal to the number at the left pointer. If it is, well then we know that we're in the left section, otherwise we know that we're in the right section. So we've differentiated between being in which section that we are in. We can then check if the target is greater than the number at the midpoint, or the target, and this is the important part, or the target is less than the number at the left point. At the left point, it means that we need to now wrap around, right? So we kind of managed to handle both cases. Then we want to set left pointer equal to mid plus 1. Otherwise, we want to set the right pointer equal to mid minus 1. Okay, so what about the second case? Well, the second case is if we are in the right sorted portion. Then we want to say if our target is less than nums mid, so it's less than nums mid, or our target is greater than nums r, in which case we want to set our right pointer equal to mid plus 1. So we want to now check on the left-hand side. Remember, we don't want to check on the right-hand side of our list. We want to check on the left-hand side now because it's wrapped around from the pivot point. Otherwise, we want to just do the same here. We want to say left is going to be equal to mid minus or mid plus 1. Sorry. Mid plus 1, this should be r equals mid minus 1. And now once our while loop is finished, we should have either returned a target or we've found no target whatsoever, in which case we will just return -1, which means that the number doesn't exist in the list. And we can see that we pass all 196 test cases for this problem. So yeah, that's the way we want to solve this problem. It's a bit confusing at first, especially to kind of understand the edge cases, what this problem description is. I will be honest, it's quite confusing. But once you look at an example, understand what the question is, asking and also just break down this problem into discrete cases, you'll understand, how do we solve this? What's the logic behind solving it? And really, you want to just think of it as a traditional binary search problem, except, we're adding these cases over here. We're first of all checking which section from the pivot point, around the pivot point we're in, and then keeping in mind that there could be the numbers being wrapped around that point. So yeah, that's basically the code to solve this. In terms of time complexity, well, it's just like, we've been told this is written in big O of log n, so it's big O of log n time, and space is just going to be big O of 1, it's just auxiliary space. So with that being said, I hope you guys enjoyed this video, and I'll catch you in the next one.